Alright, so hi everybody. It's my great pleasure today to have Lorenz Roth with us at the ÖAW for the colloquium. So I've been a quick introduction of Lorenz. First of all, he's from Bayern. I've been heard it was important to mention, so he's almost Austrian. But he did his PhD in Cologne, and he worked with Hubble data for the observation of Io and Europa, so the Galilean moon of Jupiter. He then moved to Southwest Research Institute in San Antonio, where he worked with the UV observation group as well, so continuing with Hubble. And during this time, he published a very influential paper, which was I think it was 2014 in Science, right? Where it was the first detection of water plume above the surface of Europa. And this actually, in some respect, contributed a lot to the selection of Europa Clipper, the NASA mission, to be pushed faster because of this period. So it's interesting. Then, since 2015, he then moved to KTH, the Space and Plasma Physics Department in Stockholm, where he has been based since then. And he continued working with observation of the Galilean moon, but also other planets such as Uranus. I think you're one of the PhD students who work on Uranus. And yeah, he recently became an assistant professor. So congratulations, Professor. And on this note, I think today we'll hear about Io and its role in Jupiter's magnetosphere. So, Lorenz, all right. 45 minutes. Okay.
Yes, I'll try to stick to 45 minutes. Okay, thank you very much for the nice introduction and applause and laugh I received about being almost Austrian. Actually, I have Swedish citizenship by now. This feels very wrong. So I guess I would dare to say I feel more Austrian than Swedish, but let's not go there. Okay, so I talk about the moon Io today most of the time, but I will start by introducing KTH a little bit. I guess some of you know about KTH and the Space and Plasma Physics Division through some projects, but just a brief overview on what we are and what we do. And then I talk about the moon Io and topic of the mass loss from Io to the vast magnetosphere of Jupiter. And finally, connected to this, talk a little bit of the about the upcoming Jupiter missions, really only briefly, and actually a bit how close they will come to Io, to the sun. Okay, so KTH is the largest technical university in Sweden. Its main campus is quite in the center of Stockholm, so that's really nice. I picked some two pretty pictures from summer. It's not yet summer in Stockholm. This is my warmest day this year here today. So, but it can be very warm and green in summer. And basically, here's the campus. Here's our building. And then they have this representative Borggården main building here, and the city center, and all the islands is a bit to the left. And this will be downtown, so the campus is to the right. And this is downtown with the town hall, the King's Palace, and then Nordic Museum. Here's the Reichstag. And it's all. This is kind of a 15-minute walk only from the university, which is really nice. And just for the overview on how large the university is, there are about 17,000 students. I think it's a bit less this year, but this is old numbers. 4,000 people are employed, and 300 of these are professors, and the others are the research staff, and about 1,600 employed doctoral students. Rough idea. And it's a very wide field of research and science. Its structures, it's divided in 5 different schools, all the way from architecture and building to electrical engineering, computer science, industrial engineering, and then even chemistry, a bit medical research, and the engineering sciences. And we are not in engineering sciences, where you might place us maybe first, because there's physics and mathematics. Our division is in electrical engineering, really from building space probes, and from that perspective. So this division of space and plasma physics is also divided in 2. kind of areas. Mostly it's actually space physics, and then it's the complex plasma physics simulations of laboratory plasma interaction with more walls, melting of walls, other kind of theoretical aspects of complex plasma environments. But the space group has heritage in electric field measurements and Langmuir probes, some involvement in different missions. We are on RPWI, on the big Jupiter Icy Moon Explorer. Then we also delivered hardware for MMS. And what we currently mostly do on the kind of hardware side is smaller rocket projects. And student rockets is something that kind of happens every year at KTH. But one professor also has kind of constant other efforts in building small probes for rockets launched in northern Sweden. That's a quick overview. And so myself would be represented by this picture here, because I'm kind of a bit odd in this group, since most of my work is with telescope observations of planetary objects, optical UV observations, rather than in situ measurements by spacecraft. And this is just a group picture, a bit older already, but the most recent we have. And so it's a rather small group with mostly scientists and professors, and the 2 engineers left, roughly 10 PhD students, and some part-time employees. That's about half the group you see in the picture. And that's how it that's how it looked last week, still in Stockholm. Now it's actually a bit warmer, the snow gone. Okay, then I come to the Jupiter system and the Moon Io. So we're going away from Earth, flying out in the solar system, and going to the largest planet we have. So Jupiter, it's not only the largest planet, it's also the most massive planet, but also the one with the fastest rotation, 10 hours roughly, so the shortest day in a sense, and the strongest magnetic field, creating a huge magnetosphere. Then it has many moons. I think currently, again, the most moons, it always depends on how many are discovered. At least it has the most kind of planetary size moons. If you say radius is more than 1,000 kilometers, there's 4 moons, and these are the Galilean satellites here: Callisto, Ganymede, Europa, and Io. From outside to inside, the 3 outer satellites are icy bodies, so they have a nice shell, and there's hints for liquid water under the ice shell for at all 3 of them, and then they're more or less differentiated. And going away, Europa is quite differentiated with a mantle, and then iron core. Callisto is less differentiated. And then we have the innermost of the 4, Io, which has a quite different surface. So there's no water at all, there's no ice, but it's dominated by sulfur dioxide and other sulfur components, and it's often or best known for a certain property. And you will probably always hear talks and saying that Jupiter Moon Io is and that's kind of the standard phrase to introduce Io. And it is really exceptional because it's the only body, I think, in the solar system where every time you take a picture from the same region with kind of similar resolution, it looks different than the picture you've taken before. And I would say almost all objects you take pictures of, you take a picture, years, 10 years later, it actually looks the same. Not for Io, it's always different, and I will show a few examples, and that's because of this extreme volcanic activity that constantly changes the surface landscape. So where does it come from? This goes back to the Laplace resonance, so the 3 innermost, not Callisto, at least not in direct resonance. The 3 innermost of the 4 satellites have a orbital resonance. So whenever Io orbits 4 times, Europa does 2 times, and Ganymede 1 time, which means they are aligned every orbit of Europa on different sides of the planet. And this fact keeps all of them on a relatively elliptic orbit. And then it's not the direct gravitational influence of the other moons, but instead it's the changing gravitational influence of Jupiter that creates strong tides on these moons. And because Io is closest, it experiences the strongest tides. And these tides can be summarized basically in two kinds of tides. There's a permanent bulge that is changing orientation, and then there's a diurnal bulge that basically becomes more pronounced and less pronounced on an orbit going from pericenter to apocenter, where you see kind of a less pronounced bulge. Here the bulge is more pronounced, and here you see intermediate bulge that is facing to the center of the ellipse, but not to the center of gravity to the planet at this point. So you have this variation over an orbit. And these tides are so extreme in Io that they create heat in the interior, so the dissipation and then heat, and this drives this extreme volcanism. And I show a few surface examples just because I think it's nice to see these features. This is a classical lava lake. You see many of them on Io's surface, and in high resolution thermal pictures, you even see different temperatures across such a lake. So this is fresh lava here, the black and red, and many of these lakes are kind of overturning lakes. So you have upwelling material at the rim where it's hottest, and then it goes a bit to the center, and then it goes down again. And as you can see in thermal images, this is very hot ring. It's a bit cooler, but still hot in the center. But then you have flow dominated features all over the surface, basically some source and then flowing over the surface, creating these river-like or liquid-like features.
When you talk about temperatures, so warm and hot, what kind of temperatures are we talking about?
Yes, very good. So the background surface is cold, like in the icy moon, it's like 130 Kelvin or something. And then hotspots, well, they need to be detectable, kind of in contrast to the background, but can be anything from 300 Kelvin to, and that's kind of active research. So how hot it gets, I think 1,700 has been detected, but it's kind of critical how hot kind of mass you can produce at Io. But I think 1,700 is the temperature I have in mind for the hottest detected hotspot. So you can have lava fountains even. There's a comparison to Earth. It's not always clear how to see these features in the images, especially when they're oversaturated. This is the North Pole, the Tashtar volcano. It also has a very large plume, as we will see. And this is a nice example of the changing landscape. This is from November 99 to February 2000, so just 2 months, and then you have something hot, fresh appearing on this side of the Catena, but seems to be a bit colder, and then, or especially here, it's colder as well, and then here suddenly this is cooler, but there's fresh material as surface with the rim to the left. Another visual example of this volcanism are plumes. Like I said, this is the Tashtar plume, so it comes from the region that we just saw the lava on the surface. This is one of the highest plumes. The material goes up to 400 kilometers. Of course, gravity is lower, but still it's very ejection at high velocities. And then you see this well from spacecraft flybys at some higher phase angles, because then you get forward or sideward scattering of solar lights by the dust in these plumes. And basically all spacecraft flybys where you have good imaging, you see an active plume like this. And this is a series of 8 images, but yet you see the dust grains kind of evolving and falling down. Even from Earth, in the case here with Hubble, you can detect that there are plumes. On Io, this is a known plume, so people knew that when you look in transit, so the background is Jupiter in that space, and you see the moon, and then you see the Pelé plume, which was known before, just at the limb, in absorption of the background light from Jupiter. But it's not so easy to kind of monitor, or it has not been for a long time, the volcanic activity from Earth. This was changed with the arrival of adaptive optics. Then at least you could take spatially nicely resolved infrared images, and these show the thermal emissions. And this is an example from Keck, from the Keck telescope on Hawaii. Images taken at a similar time at different kind of infrared bands. We see the central wavelength here, and then depending on the bands, you see the thermal emissions from these small hotspots more pronounced or less pronounced. So here you mostly see reflected sunlight, and here you don't see much reflected sunlight, but these hotspots stick out very much. And the program from Kepler and Declaire is kind of an ongoing, still today ongoing program, where they every time when there's an idle time on Keck in twilight, they point at Io, take some of these images. This is just from the first 2 years or so. So vertical is different wavelengths, and on the horizontal is different times. So there are lots of these images, and for one of their publications, they made a nice illustration. When you take each hotspot that is detected in these images and map the power in the hotspot on the global map of Io, and then have like a time series of observations, you can see a bit how the activity changes, and most spots kind of appear randomly and disappear randomly. You have one where you can see some kind of periodicity. It's been found about 500 days, this one here. But all the others, we don't know how they vary. It seems to be non-systematic, but it's definitely time variable. Although a non-detection, of course, can always be missing data or activity below detection level. But the bright stuff popping up would be detected in any image. So if it's not, if it disappears again, it must have disappeared or faded. So very active, extremely time variable, mostly non-systematic. This volcanic activity also is the source of the atmosphere of the moon, and it's long debate, but now we kind of know that about 50% of the atmospheric gases are produced directly from outgassing. So they're kind of these volcanic plumes or similar eject gas that fills the atmosphere. This is a smaller fraction. A larger fraction is that the volcanic gases fall out, freeze at the surface at the background temperature of 130 Kelvin, and it's mostly SO2. And then at night, it completely freezes out because at 90 Kelvin at night, and then there's no SO2 left in the atmosphere. But on the day side, you can have enough sublimation around noon to kind of re-vaporize the stuff and build the dayside atmosphere. So the dayside atmosphere is more sublimation and some outgassing. This can be observed in different ways. It was first observed by the Voyager spacecraft, but then after we have many ways from Earth to observe the SO2 atmosphere. In one paper I wanted to point out, because it's the work by Gabriel and me when he was in Stockholm, we use these Hubble observations where you see the atmosphere in absorption. So the atmosphere is concentrated at the equator, and the signal is absorbed here, and where you have signal, that's less atmosphere, and you can make a global map from many of these images and deduce the abundance of SO2 and see indeed it's a band at the equator and less atmosphere at the poles. This is also consistent with kind of the sublimation is strongest kind of near the equator over the day. But there's also a tendency for volcanoes being a bit more abundant near the equator, less abundant at the poles. So you create this atmosphere, and you find that over time, this is relatively stable. There's seasonal variations because of the changing heliocentric distance of the whole system, but there were no strong kind of transient changes detected. So it means that the volcanic activity is very time variable, but apparently the atmosphere does not undergo such time variability, at least on the detectable level.
When you say dayside, it means it faces the sun, or does it face Jupiter?
The sun. I mean, this is observations from Hubble, or any ground-based observations. You're just bound to see the dayside options. Many tests about this atmosphere are then made when the moon goes into eclipse, and signal kind of a night-side scenario. Because the moment the moon goes into eclipse, the surface cools and everything is like at night. But you cannot actually probe the night side just from a space. And these volatiles, and most likely from the atmosphere, not kind of directly from the body, populate the whole magnetosphere. So this is a sketch of the Jovian magnetosphere with the 4 moons on its orbit. And then you have Io here, and Io loses material, and this material is mostly lost in the form of neutral gas and forms neutral clouds. So these neutrals are still gravitationally bound to Jupiter, but not to the moon anymore. And then they either form a cloud kind of around Io or even a whole torus, depending on their lifetime. And after some time, these neutrals are ionized by mostly impact ionization, and then they are connected to the magnetic field of Jupiter. So we're deep inside the magnetosphere, and co-rotate with the magnetic field in 10 hours in the rotation period around the planet and build this plasma torus, which is shown in red here. And other processes can build fast neutrals. Recombination is one. Then you basically shoot out even neutrals, not only into the direct environment neutral clouds, but you just fill the whole system. And this is called neutral nebula. And you can see this actually in sodium. Sodium is just 1% abundant, but it's can well be observed from Earth. That a lot of the studies are kind of studying sodium environment to trace material coming from Io. And also the plasma torus, kind of this exchange processes in the magnetosphere, leading to effective radio transport, goes over to just the plasma sheet in the magnetosphere further out. And all the stuff is from Io, which we know it's mostly because it's sulfur and oxygen. And before Voyager, everyone was expecting actually a hydrogen-dominated, proton-dominated magnetosphere. It's a gas planet. From what we expected was its material coming from the planet. That's what we still think for Uranus, for example. But it's S and O, so it's all Io's material filling the environment. And in order to explain abundances, dynamics, and emissions from the torus, you need 1 ton per second of material from Io to kind of refill it, to re-energize it. That's a canonical number. Different studies have come to the similar conclusion about this amount, and that's kind of about 1 ton per second of material is lost from Io to the magnetosphere. So many people that study especially in the magnetospheric community, study the environment, study the plasma torus through emissions, or even the aurora, which is also connected to the mass balance in the magnetosphere, because of basically the main emission in the aurora effects where the co-rotation, this 10-hour rotation of the plasma breaks down. And there's also a footprint in the aurora that directly connects to Io. Whenever you see variability in these, people tend to say, okay, and a volcano has erupted on Io. That's why something changes in the system, because it's a kind of explanation that is beyond the field of study of this particular research. You can say, okay, this is very known that indeed volcanoes change. So you can hear quotes like this: if other types of variability can be excluded, this only source of variability might lie in the temporal variability of the Io mass loading, and mass loading being the transport from volatiles from Io to the environment basically means volcano change because of mass loading. So this is the narrative, but there were reasons, especially I said the atmosphere is stable and sublimation supported. And it's actually difficult to lose from volcanoes. I'll come to this. That we thought this needs to be closer investigated. So I give more examples. It's kind of difficult because it's strong transient changes. So this is one example of the plasma torus observations. This UV emissions, a time series from the plasma torus, and this is different ions. We can look at. I think this is sulfur plus here. So that's the normal state. It's kind of stable, and then it goes up, and the emissions go up quite significantly by a factor of 3 or so. And then this is kind of a cadence. This is singly ion And it kind of makes sense. You put more stuff in, first the singly ionized material goes up, and then the higher ionization states. So this was explained by you need not 1 ton per second, but within kind of a few days, like 10 days, you need 3 to 4 tons per second from IO to explain this. And in the same way, people observe this sodium nebula. So this is a very different scale. This is 150 trillion radii. You see the whole magnetosphere and far beyond. This is populated by these sodium atoms that you can observe. And this gets brighter, transient change for a few days in the same way. So, okay, this needs some mass input on the order of 3 to 4 times higher than normal. And even changes in the aurora are often connected to this. But from 1 ton per second to 3, 4 tons per second is really difficult. It's a lot of mass, and it's a system that it's hard to explain this significant change. So this was reason enough, and it worked to build an easy team, and so a team funded by the International Space Science Institute in Bern. So kind of meet twice and discuss this topic for a week, and then kind of find new ways to address this topic and to understand the topic. And one of the things we produced was actually this figure, and we found out that the crucial part to explain this kind of how is the loss or the transport of material actually happening, and how can it change so drastically? We have to look really close to IO, kind of how does the atmosphere lose the material. So we zoom into this region, and we find that there's many different processes that have been proposed and that might lead to escape from IO. More classical one would be the thermal escape, mostly the day side, then that you have the lighter materials at the upper atmosphere reaching speeds just to escape Io's gravity, and that would be just above the escape velocity, so they would easily be bound by Jupiter's gravity and form these neutral clouds. But it's unlikely to be sufficient. You can do modeling, and it's about 1 to 2 orders of magnitude lower than even the 1 ton per second to sustain that. So likely does not sustain the 1 ton per second. Then this would be maybe intuitive. You have these huge plumes, and you say a huge plume goes off, and a fraction of it escapes to space. But it's very unlikely because the reach is 400 kilometers. We have about 1 kilometer per second ejection velocity on a ballistic trajectory, but the escape velocity is 2.6 kilometers per second. So you're well below, even for the largest plume, escape velocity. And then you have buffering effects from the atmosphere. And if plumes are collisional, you also reduce the escape. So it doesn't really work to let particles escape from volcanoes directly at all. Then you have kind of photochemistry driven, that you have photochemical processes in the atmosphere of the molecules mostly dissociating and producing atoms. They might escape, similar to thermal escape. It's likely happening, but it's hard to get even to the 1 ton per second. But with these plasma processes, so on the one hand, electron impact, on the other hand, collisions of ions with the neutrals of the atmosphere, it should work to get a kind of 1 ton per second average mass loss for different processes, but it's kind of limited by different effects, that it's very hard to increase this process by a factor of 3 or 4. So we can basically exclude these and say this might work, but if you kind of imagine it all happens at the exosphere, you would need to blow up the exosphere a lot to change the mass loss from 1 ton per second to 3 or 4 tons per second. So at the end of 2SC meetings, we still didn't know how it works, but we wrote a review paper where we summarized kind of everything around this topic. So all the different aspects, all the way from how the volcanoes relate to mass loss, the atmosphere, and then from the neutral clouds to plasma torus, and then the rest of the magnetosphere. And to see how we know how it all links together, and that we need more research to understand how the mass transport happens and how it can change, and if it can change. There's a PhD position currently available at our institute to work on this topic. I think this is really interesting, and I'm going to show a few observations that this PhD student would work on, because we had a good opportunity now with the Juno spacecraft to address a few things on this topic of mass loss. So the NASA Juno spacecraft was a planetary mission, so for Jupiter, not for the moons at all. You can see in this trajectory plot here, the prime mission. The trajectory was like this, that Juno stayed far away and then diving close to Jupiter only briefly, and then went far out again. But after the primary mission, they lowered the inclination and had flybys at all the moons. And the further Juno goes in, the more it experiences harsh radiation. So Io was already high risk, but it's the end of the mission. And spacecraft is still alive and did 2 flybys here in December last year and February this year. And this would be a chance. So Juno was at least in 1 flyby kind of in the wake of Io, so to measure in situ particles escaping. But there's no instrument to measure the atmosphere at all on Juno. There's an infrared instrument, but it's not capable of measuring SO2 or any other atmospheric species. So there was kind of a large coordinated campaign for different observations from Earth to support the Juno flybys, mostly by, in this case, measuring the atmosphere, but also an Aurora program and the radio program. And most of these programs really wanted to observe during the flybys, which did not really work out for different reasons. One was, most exciting was actually this flyby, because of the perfect geometry in terms of Juno and observing from Earth. Everything was set up for this Hubble program. I'm most heavily involved in this one here, communicate about exactly what Hubble should do, exactly what minute. Then you get an email on 29th of December saying there's software issues and Hubble shuts down for 2 weeks. But you have some data close to February 3rd. But it's a pity. So this is an example of data from February 2nd, and this is the type of observation we often use. So it observes the moon through a slit, and then you get an image within the slit of the moon. You disperse the light and project it on a detector, and have kind of a trace of emissions from Io at different wavelengths, and then your emissions are sufficiently apart, you get individual images, and that's what you kind of see here. So you see Io in oxygen neutral emissions, sulfur neutral emissions, and then you see sulfur plus, sulfur triple plus. This is kind of this where you see SO2 absorption, and this all at the same time. And this is not the first time. There have been many observations of these, but we were hoping to kind of having these in situ measurements and find out more how it connects. This is very fresh. And then I come to the Jupiter missions at the end, which you're probably well aware of, at least this one, the JUICE mission by ESA, launched last year. Myself, I'm involved through my postdoc at Southwest Research Institute in the UVS instrument, and they built the UVS instrument for JUICE, similar to many other missions in this group. And then since I moved to Sweden, I got involved with the radio and plasma wave instrument built in Sweden. With the consortium is led in Sweden, has been built in many places, and there's another Swedish instrument, Juno, also from the Institute of Space Physics, but up in the north in Kiruna. So Jupiter JUICE is on its way, will arrive here in July 2031. There's still a few years to go. And the other mission that is kind of developed simultaneously, there's all the history of a joint mission which never happened, but then the NASA and ESA have developed their separate missions, which are on a similar timeline in the end, as we will see. And the Europa Clipper is really has one goal. This is kind of habitability of the moon Europa. And as in contrast to JUICE, there are no magnetospheric or objective on the other moons. It's really Europa that the mission is focused on. It has a similar instrumentation. I didn't see other about JUICE, but it's kind of the almost identical UBS instrument. There's a radar instrument on board. There's a simpler plasma instrument, Faraday cup on board, and of course they have a wide narrow angle camera, wide angle camera. They also have a thermal imager here and an infrared spectrograph, mass spectrometer that's quite similar, magnetometer. There's one instrument that we have not on JUICE, it's dust detector, the SUDA instrument, which is for habitability things interesting. But this is actually quite interesting to study IO also, because the instrument detects bigger dust particles from the surfaces of the moons that can travel through the magnetosphere and then get broken up in the detector and mass spectroscopy of the broken apart dust grains. And you can do this from far. So you can, IO has the dust volcanoes, and we know that a lot of the dust in the system comes from IO. So we can learn a lot from SUDA. And yeah, the other thing is that so it's a similar timeline. Is arriving slightly before JUICE if it is launched successfully later this year. So there's uncertainty that we don't have anymore for JUICE. So these are the trajectories in the system. If everything goes well, they are at least about 4 years in the system together. We have multi-spacecraft, and there's a working group now kind of to coordinate things between JUICE and Clipper now that everything has been decided and will happen. And here you can see again, light blue is JUICE. So it has, if you look a bit into the equatorial bit from atop, but you are still in the equatorial plane. And Europa Clipper stays in the equatorial plane and has kind of an elliptic orbit with the pericenter kind of always in Europa's orbit here. JUICE, in contrast, has this phase high inclination because it has magnetospheric objectives as well. It wants different angles and different positions in the magnetosphere. There's a couple of nice opportunities, and this is also from the perspective of UV observations. So you have small UV telescope on both spacecraft, and usually it's very hard to break the degeneracy of a line of sight observation. I mean, you measure all the UV photons that are produced somewhere along your line of sight, but then you have two perspectives, and you can even do spacecraft to spacecraft observations. So you can probably get unique measurements of abundances of atoms and ions. And then there's one flyby, this is Europa, and these are the two spacecraft where they are really close. You can possibly take pictures of each other while approaching and going away from Europa in July 32 here. And this is pure coincidence. So this is just the missions that they're planning, and then found out that this might happen. But Clipper is not launched yet. Now for IO, it's kind of, I mean, disappointing because if you look from above in the system, so now you look on the north pole of Jupiter onto the equatorial plane, that you see the spacecraft really, they don't want to be anywhere kind of inside the orbit of Europa. Clipper, I mean, has Europa as the main target, so it has to touch the orbit of Europa all the time, but doesn't really want to go inside. And IO is here. So none of the spacecraft will be really close, which means camera observations are not that great. UV observations can do kind of the IO torus and stuff, but not the moon itself. The dust detector will still have interesting results when kind of differentiating dust composition and dust trajectories. but it's not, it's not kind of close IO science will not happen with any of these two missions. So maybe there will be a dedicated IO mission at some point. Efforts, as far as I know, have been made only in the US for US missions, and the most recent one is the IO Volcano Observer. Alfred McEwen was PI, and it was studied in phase A in the last discovery program, where it was not selected. The two Venus missions were selected, but that's kind of overcoming this hard radiation environment by having a few flybys, kind of a bit like Europa Clipper. You stay away for a long time, and then you come close to the moon and dive past the moon to the other side of the radiation belts in torus. And then you have like 10, 15 flybys where you need to do all your science. And when I read the Voyager 2050 senior committee report, so when ESA had, I think it was 2.5 years ago, released this report from the senior committee after a couple of years of looking at all the possible large class missions. They said the next large class mission should be an outer planet moon, and the driving science objective is habitability. But the report mentions IO science explicitly in kind of one of the exclusive lines. So it says outer icy moons here first, and then especially these two, or the Jovian system again, and then it's IO science. So IO is considered important. Still, I think. Now a few weeks ago, there's been another report from an L4 committee I was part of, where we should narrow down this mission to an icy moon in the outer solar system recommended by the senior committee. And we found that Enceladus is the most attractive body science-wise, and kind of the least covered body in terms of upcoming missions. So that's the recommendation in this report. So this means, in a way, this L4 mission probably going to Saturn and not to Jupiter. So this means IO will still be not visited. So maybe that's something for an M-class mission in the future, even M8 if it happens. Anyway, I think this is a very interesting body. That's probably not life on IO. So they can tell us a lot about planet evolution, planet driving dynamics. And it's a very alive object that's cool to study. Okay, thank you very much for your attention. Questions?
Maybe the elephant in the room. I mean, by the end of the day, it said the mass slots change in a couple of days, and in principle only be changed somehow in the interaction of the plasma environment, the ion environment to IO atmosphere. Is there any candidate hypothesis why this would happen sporadically and increase by a factor of 4 at least?
I mean, not quantitatively. I think qualitatively, what people have in mind is that you simply increase the amount of atmosphere over a certain period of time, and that is sufficient, that kind of this process of plasma colliding with the atmosphere is enhanced in the same way. So but not quantitatively, because, yeah.
So basically you're saying the drivers internally. So it's IO basically that somehow replenishes the atmosphere and opens up the atmosphere?
Yes, well, mostly because of the lack of any other explanation. I mean, you can do estimations, and that's what we did a bit, that you just increase the energy in the plasma or something. So there's more energetic plasma suddenly, maybe transport from out of the magnetosphere. You transport very energetic plasma instantly, but it's not sufficient. It doesn't work to create these amounts.
But what you're saying is that kind of two-step process might be difficult. So volcanism kind of replenishes the upper atmosphere, and then there's some plasma mechanism or whatever that actually takes it from there. So once the volcano gets off and gets the atmosphere populated, then you lose, but not by volcanism itself, but by some other mechanism.
Yes, that's likely. Exactly. That's. You still don't have direct escape, but you need to change the atmosphere.
But if you have dust from the moon, so the dust is remaining at the same trajectory around Jupiter. So if you have the volcanic material at the height of 400 kilometers, can this dust interact with the volcanic material in collisional interaction? Can it take away the volcanic material from the moon?
Okay. Collisions of dust particles that orbit Jupiter with gas particles.
Yeah.
Yeah. I would think the dust is not sufficiently dense or abundant, but that's just a feeling. And
But then you also say it is difficult to actually bring up gas into thermal escape, basically removing it to bring it to a height of 400 kilometers. I mean, that's what you're saying, that there's so much buffering that it's very difficult for a probe to reach in out that far.
Well, we know that the dust particles reach 400 kilometers in a plume. So we can say, in analogy, if the gas kind of entrained, and that the dust particles are entrained, then must have similar dynamics to some extent. So.
When you discussed mechanisms of mass extraction or ionized mass extraction, you probably mean but didn't mention the effect of unipolar inductor in the moving system. Reference frame of the planet, there will be an electric field which will polarize the ionized fraction, and it's a known effect that this is the mechanism how the IO tube current system is built, but the material, the charged particles which provide these currents are not necessarily only massless electrons, but also ions. And these carrier ions will also contribute to the global electric current system moving, and then we will naturally get the mass escape.
Yes, so this is quite well. It's characterized to some extent already from Galileo measurements, kind of how much mass you can lose through direct ionization at the moon. If you ionize stuff,
you have it ionized, but then the current is built because of the electric field in this system of the ion. And usually, yes, the current carriers are electrons, but also ions will fill this electric field. They will move as well. And this might be
along the magnetic lines. There's no net transport of mass along magnetic field lines. But I mean, the general understanding, and I think this is kind of back to Galileo observations and stuff, is that you can only, and that's also how you kind of explain all the torus observations, that the majority of the mass has to go through this kind of leaving Io's gravity as neutrals, and then being in orbit, and then being ionized. And that's where this 1 ton per second actually comes from, because people observe the emissions from the torus and say, like, how much of an ionization processes must take place to at the same time create these emissions that we observe. And that would not happen if it's ionized at all. So
but in any case, as far as you have an electric ionized material, then you will polarize it.
Yes, true. I mean, that's a bit what I meant by buffering. If you change the basically this is this plasma interaction. You have the incoming plasma, and you have it's like a co-rotational electric field in the rest frame of Io. It's short circuited, and the incoming plasma is diverted around the moon, so that the interaction is actually happening kind of at this surface of this curtain that goes around Io. If you increase the atmosphere, you just open the curtain a little bit more, but the tangent point of the magnetic field lines, kind of the curtain edges that touch the atmosphere, are not that different in a way. It's not kind of to scale up the mass loss by 3. You need to increase.
But the modulation of the mass load is could be due to volcanic activity. So first step. The question what happens there.
Are there any like relation to solar activity, UV flux ionizing that far away? Probably not, but the sun is quite variable. So was it in any, because I understand that all the measurements are done either in the torus or on the aura footprint, saying okay, we get more flux, so therefore there should be more mass loss from somewhere, or let's say ions in the system. But it's really just ions in the system, so the density of ions in the system somehow increase. And everyone thinks, okay, it's from the IO, but is there?
No, there's no. You mean that you mean there's some solar event?
Something external should
happening before something like this happens.
Yeah, or in the sodium nebula, because these are really like global picture of it. And yes, you can say it's from IO, something happened in IO, but it could also whatever. The observable is that there is more ions in the system. Where we come from could be different things, right?
Empirically, it has never been, almost never a clear coincidence. And theoretically, it's quite, it's considered not important for the ionization as compared to electronic ionization. So it's a self-sustaining system, no way without the sun, except for creating the atmosphere.
Question: does one know how much of the Io surface is actually warm? I mean, warmer than warm in order to be liquid. So what I'm basically asking, does one know how much of the iron surface is above sublimation temperature? Because then there would be an evaporation of the surface, which would give you another mass replenishment into the atmosphere.
I don't know exactly, because I mean this is from Earth, and then you on this kind of spatial resolution you could say all this background here is basically you don't have any thermal emissions, and if you're above some threshold surface temperature you would have thermal emissions. This can of course mean there's small patches. There's more high resolution observations from Juno now, infrared camera. Let's see all these lakes. I don't know exactly what is the fraction really fresh lava to the global surface.
I was just thinking magma ocean. There's one of the topics in exoplanets. You maybe have tiny magma oceans here, which could change the atmosphere.
And that's, I mean, that's kind of the other problem that I didn't go much into detail about. It has never, I mean, there are different observations of the atmosphere, and we see seasonal effects. So some people observe IRTF every twice or 3 times a year over now 2 decades. IO, they see the SO2 atmosphere, and they said it's always there and just average. They said, and it changes seasonally. That's nice. You can see it goes. It's fainter. It's diluter when IO2 is further away from the sun. It's a bit thicker when it's closer. But you never see a spike or so, or a dropout. It's just always there, the atmosphere. And I think you should, to have this drastic change of 4 in the mass loss. But that's in everyone's mind, kind of, you need to have some change in the atmosphere that should be observable, but it has never been observed.
Is it understood why there is only SO2 basically emitted? Why not anything else? Why not CO2 or water or whatever?
Yeah, well, CO2 has lower sublimation points. So CO2 is probably lost over solar system evolution. Water also. Yeah, other
I mean,
volatiles.
if you ask anybody without knowing it, would anybody have guessed that this kind of object should produce SO2?
Maybe yes. I think it's on Earth. It's one of the gases that are used to trace kind of volcanic activity. It's not a primary species in volcanic outgassing, but it's used quite a lot as 10% level. So maybe if you take out the other that you just mentioned on Earth, it's H2O and volcanic gases and CO2, then you're left with this less volatile. And the volcanoes also spit out S2 and other sulfur compounds, but they either kind of, I think, freeze forever and then cannot be reactivated, or they get lost quickly.
That's also why the surface is so yellowish. So you have this.
That's SO2.
Sulfur comes down, deposits, and then you have this strange surface.
I mean, maybe tangentially on this. I mean, the other activity of Io was actually predicted before Voyager went there and basically confirmed it. And this activity except SO2 because it's just it's the last remaining survivor basically. Everything else is just gone.
I wonder whether it has to do with that sulfur is actually very heavy, so it's not so easy to actually expel it. So maybe on the long run you can use maybe carbon or whatever, but sulfur is maybe more bound somehow to the system.
Sorry, you want the other question before?
Yeah.
Okay, so Ruth first and then, sorry.
If I remember correctly, there's this hypothesis that some of the orange brownish features on Europa are caused by material coming from Europe. So if Clipper is coming by close to Europa and has instruments like Juno on board, will it be able to detect dust or whatever material coming from Io, and will it be able to distinguish between Io and Europa material?
Yes, absolutely. I think that's one of the plans. There's even some research now on base results constraining if this works to actually have sufficient transport from Io to Europa to make these patches. And I don't remember this all. I think it's hard actually. It's not clear that it's possible to transfer enough material to cover the surface.
Last question.
We have a lot of Io volcanism, but volcanism should be accompanied by earthquakes. When that gets Io quakes, have you seen something? Because this gives you a lot of energy release.
Yes, there are no plates on Io in the same sense. There's no plate tectonics. So you don't have earthquakes.
But the crust is not.
Break of plate tectonics.
Yeah. So if anything, I mean, we don't. I mean, and that's another the magma ocean. I mean, it's another topic that's not settled. I think we don't actually know the exact kind of crust structure and state and phase state, even how much is molten inside.
I mean, that's
So
like the magma ocean overturning. That actually could maybe
the lake,
that there's something internally happening which you actually don't see, and that heats up or replenishes somehow to outgas in the atmosphere, and then you won't necessarily see it because it will be very diffusive thermally, but it will maybe emit a lot of gas, but that's very difficult to model.
So we see it's going in transit, you would see the absorption, right? The current density of whatever is there. If it's very dense, you will see it. Even if it's diffuse, you will not see in the thermal.
Yeah.
But every time Io have transit observation, you might see, we would see a fuzzy ring.
Yeah.
So I mean,
No fuzzy rings.
No, I don't have the plot here. Since there's this nice kind of almost continuous monitoring now, we do have at least this kind of observation before people see something changing in the magnetosphere. And there's no way of seeing in this data of the hotspots that something has particularly changed before the magnetosphere changed. So I mean, if this would be another kind of clear evidence, if you have some amount of hotspots appearing and disappearing, and suddenly there's 10 times more over 1 month, of course, then, but this is not what we see. There might be a new hotspot the day before the plasma data changes, but I mean, it's every week a new hotspot. So
But hotspots in my ocean, like, I mean, they are different, right?
yeah, no, I'm just saying, if you have something periodically overturning and that has a chain of reactions changing in the sphere and changing, then you would also want a piece of evidence on the surface somehow.
Yeah, that's true.
Thank you. And maybe last question. If you lose 1 ton or 3 tons per second, how long would it take for this long?
I should know the number. Yeah, there's a couple of 100 million more to survive for Iowa, so that's okay. I don't need to be worried. But it's still more than us. Those are some big closes.
Thank you very much.